Hi there and welcome to another video from HEGARTYMATHS. It's a Maths A-level video here and we're talking about integrating standard functions. So what I'd like to do in this video is I'd like us to be able to integrate some standard functions and the way we're going to do it is by reversing the differentiation process. Now these are the functions I'd like us to be able to integrate at the end of this video. So firstly, functions of the form y is equal to x to the power of n, which are polynomial functions. I'd like us to be able to integrate those functions. Also, y is equal to e to the power of x. So exponential functions, I'd like us to be able to recognize the integrals of exponential functions. Next, I'd like us to be able to integrate functions such as 1 over x. Okay, so reciprocal functions. I'd like us to be able to integrate reciprocal functions. And then I'd like us to be able to integrate trigonometric functions. So standard trigonometric functions like y is equal to cos x, and I'm going to put here trig functions, but they would include all the standard trig functions that we need to be able to integrate. So that's what I'm attempting to do in this video. Okay, so we're going to start off with the big idea about what is integration. And this is going to help introduce the idea and how to do some of the integration techniques. Before we get to integration, let's talk about differentiation. Now, suppose we had a function, for example, y is equal to, let's say, x cubed. Now, if we differentiate this, we differentiate both sides. So what I could do is I could then say, imagine we differentiated both sides. So I'm going to differentiate this and differentiate this side. What would we get? Well, we'd get the gradient function, which we denote dy by dx, and differentiating a polynomial, I multiply by the existing power, which is 3, and I keep the function as it is, the x, but I reduce the power by 1, so it'd be 3x squared. Okay, so this here is all the process from here down to here is the process of differentiation. Now, the big idea in this video is that integration, the process of integration, is the reverse process of differentiation. In fact, sometimes integration is given another term, it's called anti-differentiation. It undoes differentiation. Okay, so this is the big idea. The question I'm going to ask here is, suppose we started off with a function that was a 3x squared, and for now I'm going to say it's dy by dx. What would have differentiated to this? What function would have differentiated to this? Now we know that the function would have been an x cubed function, but in fact, it could have had any other number in the world. Say if it had a 2 here, this would have still differentiated to this because a constant differentiates to 0. Or if it had a, I don't know, a negative 8 here, the answer would have still been the same. So when we integrate, we actually get a constant of integration as well, plus c, I'm going to call it. So this process of getting from the derivative back to the original function is called integration. So this here is called integration. And that's the big idea here, okay? So the process of integration undoes differentiation. It brings us back to the original function. Or the way we can think of integration is we can think of it as trying to find out what function must have differentiated to this answer, okay? So that's the big idea we're going to use in this video. Also, the big idea is that whenever you integrate, you get yourself a constant of integration. Now, I just want to take a second to just show you a bit of notation for when we do this. Say we were given an original function. Say the function was something like y is equal to 3x squared. We're given some function. Now, forget about being the gradient, etc. If I want to integrate both sides with respect to x, x is my variable that I'm integrating with respect to. This is how I would denote it. I would say I'm integrating, this here means I am integrating the function y with respect to x. So what I'm going to do is I'm going to integrate this 3x squared, and you always have to state with respect to x. And what would the answer be? Well, we said the answer would be x cubed plus a constant c. So the integral of y with respect to x is x cubed plus c. Okay, and that's how we write the process of integration here. Up here I just showed you that integration was thinking about what function differentiated to your answer. This is how you would actually write it. If someone told you, here's your function, integrate it, that's how you would write it using this symbol here. Okay, so let's start by thinking of all the functions we know how to differentiate and using those ideas to be able to integrate. So first things first, say we had a function y is equal to x to the power of n, and we wanted to differentiate this. So say we are going to differentiate this, we would get that dy by dx, the gradient function, is equal to nx to the power of n minus 1. That's something we should know from previous results in our pure maths. So, applying integration, suppose I was given the gradient function and it was nx to the n minus 1, and I integrated this, the result I would get is I would get my y back and I would get x to the power of n, but this time plus a constant, because any number here that I had on my x to the n would have differentiated to 0. So let's try and generalize this rule. So this was just showing that it's the opposite of this. Suppose someone gave me a function and they said that f of x, I don't know, f of x, some function of x, is x to the power of n, and they wanted me to integrate that function. So I'm going to integrate this function with respect to x. What answer would I get? Well, how do I undo the process? When I differentiated, so let's write differentiate here. The two steps I did was I multiplied by the power, I multiplied by the n, and step 2, I reduced power by 1, so n became n minus 1. And so when I'm integrating, I'm going to undo this process. So to undo reducing by a power of 1, step 1, I'm going to increase power by 1. And step 2, I'm going to divide by the power. So here, when I'm integrating x to the power of n with respect to x, what am I going to do? I'm going to increase the power by 1, so I'm going to get x to the n add 1, and I'm going to divide by this n add 1, so it would be 1 over n plus 1, and then plus a constant. So the integration sign is removed because I've done the integral, and the integral of this function with respect to x is as follows. So this is a result I need to know. If I have a function x to the power of n, when I integrate that function, the result is x to the n plus 1 divided by n plus 1 add c. Okay? Okay, let's think about exponential functions and what happened there. When we had y is equal to e to the power of x, and we differentiated, we got that dy by dx was also e to the power of x. So, if I took that differential, e to the power of x, and integrated, what would I get? Well, I'd get my y back, I'd get e to the x back, but I'd also get constant of integration. So in general, the general rule is, suppose I had a function of x that was e to the power of x, and someone asked me to integrate that function of x with respect to x, I'd integrate e to the power of x with respect to x, and I would get e to the x plus a constant. Okay, so the integral of e to the x is e to the x plus a constant. Okay, let's think about logarithmic functions. When I was differentiating and someone gave me y is the natural logarithm of x, and I differentiated this, I got that dy by dx was equal to 1 divided by x, the reciprocal of x. So, if I was starting off with the gradient function being 1 divided by x and I integrated this, what would I get? Well, I'd get that y is equal to the natural logarithm of x plus a constant. Okay, so in general, if I was given a function of x that was 1 divided by x, okay, or x to the negative 1 here, and I integrated this, so I integrated f of x with respect to x, so I integrated 1 over x with respect to x, I would get the natural logarithm of x plus a constant. So the integral of 1 over x with respect to x is this here. Now notice I can't use the polynomial rule here. With polynomials, you remember I said you add 1 to the power and divide. If you added 1 to the power here, you would get x to the power of 0, and dividing by 0 would give you would not give you a defined result, so you can't use that in this case. So when you're integrating 1 over x, you get natural logarithm of x plus c. And lastly, I want to finish off with the trigonometric functions. So here are the results we had from differentiation. If y is equal to sine x and we differentiate, we got dy by dx was equal to cosine x. When we had y was equal to cosine x and we differentiated, we got that dy by dx was equal to negative sine x. When we had that y was equal to tan x and we differentiated, we got that dy by dx was equal to sec squared x. Okay, and the other results we got that when y was equal to cot x, which is 1 over tan, and we differentiated, dy by dx was equal to negative cosec squared x. And we had that when y was equal to sec x and we differentiated, we got that dy by dx was equal to sec x tan x. And lastly, when y was equal to cosec x and we differentiated, we got that dy by dx was equal to negative cosec x cot x. And they were all the results that we were expected to know in for differentiation. So let's try and generalize the rules going backwards. If I was to integrate, so if I had dy by dx is equal to cosine x and I integrated, I would get that y was equal to sine x is my answer. So in general, the integral of cosine x with respect to x is sine x but plus a constant. We would have had plus a constant, and that's the result I need to know there. Okay, so if I had dy by dx was equal to negative sine x and I integrated this, I would get that y is equal to cosine x plus a constant. So if I was integrating negative sine x with respect to x, I would get cos x plus a constant. But suppose I was just making it more simple. I wanted to integrate sine x. If I integrate sine x, that must be negative cosine x but plus a constant. So that is another result I need to learn there. Okay, then keeping going forward with this, I'm sure you'll get the idea. I'm not going to write each step down, but if I integrate sec squared x with respect to x, going backwards, you can see that I get a tan x plus a constant. Another result I need to learn. If I'm going to integrate negative cosec squared x with respect to x, you can see going backwards, I'm going to get cot x plus a constant. But say if I want to keep everything positive, if I'm integrating cosec squared x without the negative, you can see I'm going to get negative cot x plus a constant. That's another result I need to learn. Suppose I'm integrating sec x tan x with respect to x. Going backwards, you can see that I'm going to get sec x plus a constant. And lastly, just underline that, another result I need to learn. And lastly, if I'm integrating negative cosec x cot x with respect to x, you can see that I'm going to get cosec x plus a constant. But say if I wanted to keep this side positive, if I'm integrating a positive cosec cot, I'm clearly going to get negative cosec plus a constant. And that's another result that I need to learn there. So these here, that one, the 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 results are the results I need to learn for trigonometric functions. So let's just recap everything here. Let's think about what we've learned. When I'm integrating polynomials here, the integral of x to the power of n is, so actually I might do this on a separate page. These are what I've learned. So if I'm integrating x to the power of n with respect to x, I would get 1 over n plus 1 x to the power of n plus 1 plus c is the answer. If I'm integrating e to the power of x with respect to x, I would get e to the power of x plus a constant. If I was integrating 1 over x with respect to x, I would get the natural logarithm of x plus a constant, and then the various trig ones that I talked through. So if I'm integrating cosine x with respect to x, I would get myself sine x plus a constant. If I'm integrating sine x with respect to x, I would get negative cosine x plus a constant. If I was integrating sec squared x with respect to x, I would get myself tan x plus a constant. If I was integrating, I'll go along here for the other trig ones. If I was integrating cosec cot x with respect to x, I get myself negative cosec x plus a constant. If I was integrating cosec squared x with respect to x, I would get myself negative cot x plus a constant. And lastly, if I was integrating sec x tan x with respect to x, I would get myself sec x plus a constant. Okay, and they are all the integrals, the standard ones I should recognise. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9. And they're all about knowing the differentiation, really. You don't really have to remember the integrals. If you can remember that if you were to differentiate this, you'd bring down the power and reduce the power by 1. That means when you integrate this, you get to that. If you can remember that when you differentiate e to the x, you get e to the x. If you integrate e to the x, you get e to the x plus c. If you can remember that when you differentiate logarithm of x, you get 1 over x. If you integrate 1 over x, you get logarithm x plus c. And similarly with the trig ones, if you can remember when you differentiate sine, you get cos. When you integrate cos, you get sine plus constant. If you can remember that when you differentiate cos, you get negative sine. When you integrate positive sine, you get negative cos plus a constant. And all the others apply similarly. So they're all the rules we've gone through. Let's try some examples. Here's the first one. So we want to integrate this. Now with integration, you will have learned in core 1 and core 2, you can integrate each of the summands separately, each of the things being added together separately. So the first thing I would always do is I would break this integral up into the integral of 2 cos x with respect to x. You must always explain what you're integrating with respect to, plus the integral of 3 over x with respect to x, plus the integral of the square root of x, which I'm going to write as x to the power of a half with respect to x, like that. The next thing I always like doing is take out a factor in the integral. So take out that factor and take out that factor. It makes the integration easier. So I would write this as 2 lots of the integral of single cos x with respect to x, plus 3 lots of the integral of 1 over x with respect to x, plus, there's nothing to take out there, so x to the power of a half with respect to x. Now, when you integrate each of these, they're all going to get their own constant, but you can just write one big constant at the end, so don't worry about the constants till the end. So let's have a go at integrating this. Now, integrating cos x. Remember, when you differentiate sine, you get cos, so when you integrate cos, you get sine plus a constant. So this would be 2 sine x plus a constant, but I'm going to write the constant at the end. What about this one? You've got 3, and what about when you integrate 1 over x? Well, when you differentiate logarithm x, you get 1 over x, so when you integrate 1 over x, you get natural logarithm x, so it would be 3 natural logarithm of x. And lastly here, this is a polynomial, so to integrate a polynomial, you add 1 to the power, so it would be plus x to the power of 3 over 2, and you divide by 3 over 2. 1 divided by 3 over 2 is 2/3. What are we missing? We're missing plus the constant. So the answer to this integral here is 2 sine x plus 3 natural logarithm of x plus 2/3 x to the power of 3 over 2. Now, one thing to note here, natural logarithm of x, if you remember what the log graph looks like, remember the log graph looks something like this. Log is not defined for when x is negative. So what we do, we tend to always do this. When we get a log from this, we always put a modulus around it like that to ensure that x is a positive. Any x we put in will be defined for natural logarithm, okay? And that's the answer. Okay, let's have a go at one more example. Obviously, you can try this if you want in advance, but I'm going to go through this. So the first thing I always like to do is split up the integrand. So they're in two different parts being subtracted. So I'm going to write this as the integral of cosine x divided by, I'm going to split sine squared into sine x multiplied by sine x, and tell that you're integrating with respect to x, subtract, and I'm going to take the 2 out in one move, integral of e to the power of x with respect to x, like that. Now, a little trick here, you can put in a multiplied by 1 here, a hidden multiplied by 1. Now, cos x, this cos x divided by sine x is going to be cot x, and 1 divided by the sine x here is going to be cosec x. So what we've got is we've got the integral of cot x cosec x with respect to x, and subtract 2 lots of the integral of e to the power of x with respect to x. Now, we should be able to do this integral. This is one we should recognize. We know that when we differentiate, if we were to differentiate cosec x, what do we get? Well, we get negative cosec x cot x. Okay, so therefore if we integrate negative cosec cot x, if we integrate negative cosec cot x, we should get cosec x. What if we were just integrating positive? Well, our answer should be negative cosec x. So this is a standard result we should remember, and the answer to this is negative cosec x, and the integral of e to the power of x is e to the x. So we get subtract 2 e to the x. Notice the integral signs are gone once we've done the integration, and don't forget to add your constant, add c, and we're done. So they're the two examples I wanted to do. These are the, just going up here, these are the 9 results that you need to learn, and with those results you should be able to do the following questions. Exercise 6a, page 89. Thanks very much for watching.